Hello, I'm Claire Gilliam, and this is my presentation on lab number 3 about circuits. First, we have our introduction and the main physics principles we used. So, what was this lab's purpose? Well, we wanted to observe a circuit and measure its values of resistance, voltage, and current. The tools we used to do this were, we created 2 circuits. They composed of wires, conductors, a multimeter, and batteries. The physics principles used were Ohm's law, which states that voltage is equal to current times resistance. Loop rule, which is just an aspect of the conservation of energy, and it says that the change in potential is equal to 0 for a loop. And the node rule, which says that the current flowing into a node will be equal to the current flowing out of the node. The lab's results were we were able to predict the current of the circuit and find it. However, our predictions didn't exactly align with the real-world values for voltage and current that we found. For our experiment and observations, for the first experiment, our assumptions were there no wires or other components had any internal resistance, and defining our system, we defined the system as the circuit and their surroundings as everything else. Okay, so running the experiment, we created a circuit and a loop, exactly like the one pictured here, where we measured the current at I1 and I2, and we had 2 resistors, 47 ohms and 100 ohms. So we created the circuit, then we collected the ammeter readings at I1 and I2, and then we collected the voltmeter readings using the multimeter as well at the same position, and our circuit looked like the one you see there. So our findings were that the voltage V1 was equal to 0.92 volts, V2 is equal to 1.99 volts, and that means that the total potential is equal to 2.91 volts, and this is a little off from our predicted value of 3 volts. However, we will talk about the errors later. Our predicted current value, which would be 3 divided by the sum of the resistors since they are in series, so we would get 0.019 amps. However, our real-world findings were that the first current was 0.018 amps and the second was 0.0201 amps, and then we were able to find this graph. At each position, what would the voltage look like? And so we see it spikes up and then it decreases as we flow through the circuit. For our second system, we assumed that no wires or other components had any internal resistance as well, and we see that the system is still the circuit, the RC circuit this time, and the surroundings are still everything else. So our procedure for experiment 2 was we assembled a circuit like the one you see here with 2 1.5 volt batteries, 2 light bulbs, and a 1F capacitor. And then we connected the capacitor to one of the bulbs and observed the light bulb's brightness over time. And then we removed the capacitor from the battery so it was no longer getting charged and observed the light bulb's brightness over time after we removed the capacitor from the battery. Okay, so for our findings for this circuit, we found that the 40 ohm bulb took 58 seconds to charge and 41 seconds to discharge, while the 10 ohm bulb took 11 seconds to charge and 10 seconds to discharge, which makes sense because the 40 ohm bulb, or the bulb with the higher resistance, will take longer to charge. So errors running this experiment. So there are possible errors because our predicted values and our ideal values and our measured values were different. This could have possibly be because there was some resistance in our equipment like the wires or the multimeter. Our timings could have been inaccurate when we timed the brightness of the light bulb, and the multimeter could also be inaccurate in its actual measurements. Finally, we have a discussion and conclusion. So, concluding questions. What if we charged the capacitor without a resistor? Well, in theory, if we charged it without a resistor so it had no resistance, the capacitor could charge instantly. However, this isn't possible as we did actually have to have a resistor, and we won't ever have 0 resistance in our loop. Thank you.